had a manageable weekend. Otherwise, maybe not the best of weekends, but manageable at least. Reminder that we have our in-class quiz on Thursday. Okay. Be about 5 or 6 questions, similar in nature to the problems that we've seen out in textbooks. I'll write it to basically last for 45 minutes. So you'll have, you'll have the whole 50 minutes to take it. I said we would speak a lot to find the hardest questions you can find, so we'll go back to Wednesday. And then whatever you find, I'll put on the quiz. So that's the plan. Right. As I said, he's not going to be here until Thursday, so if you have any questions, I'll hold. I think I can hold my office hours at the time he usually does, so just stop by and see me. I still have yet to see anyone in my office hours this year. It's very hurtful. You came in to turn on your computer, and that was it. It's very hurtful. Come on, I'm not that bad. I'm not that scary. Maybe not. Please come see me if you have questions. I encourage you to look back over the 2 online quizzes that we've had, sort of review what kind of mistakes you may have made there. That'll be a good way to start your studying. Don't wait until Wednesday night to start studying. You should be studying for the quiz now. So go back and look over the old material. Make sure you keep up with the new material as well. Right? Okay. And with that, we will go ahead and start in material for today. So last time we started talking about rates of change, and we started looking at how to calculate rates of change with the idea that we're trying to move towards finding something like instantaneous rate of change. We talked a little bit last time about how we can use a little table to try to estimate rates of change as we get closer and closer to specific instants in time. Okay. Today what we're going to do, alright. I'm just going to start class. But hey, good. I'll wait. It's good. Pencil out. Come on. Hurry up. Pencil out. Let's go. Alright. So, last time we looked at some notation and stuff. And, today we're just going to do a little bit more in this section before we move into the next section. We talked about rates of change, and in terms of notation, what you'll often see, rates of change will often be written in this format, delta y over delta x. Now, when you see this, this notation is familiar because it should bring to mind slope of a line. And that is essentially what we're working towards, is we're working towards finding slopes of lines, because slopes of lines sort of give us a way of identifying how fast something is changing, giving a sense of what rate of change means for us. Now, if we look sort of graphically, I think we might have seen this picture last time. Graphically, what we have is we have some sort of graph like this, and suppose we're interested in this point right here, time t equals 1, and what I want to know is, at that specific instant in time, or that specific place on my graph, how fast is the graph changing? How fast is it changing? Using this notation, using this concept of rates of change, what I'm doing is I'm looking at slopes of lines. We saw last time when we drew that little table up that as we shrink that point out there closer and closer to the value we're looking at, as we get this point closer and closer and closer to our point here, essentially at some point in time, what we get is we get what's called the tangent line. And the tangent line has lots of properties that we'll look at a little bit later. But essentially, if you were to sort of zoom in, if you were to imagine graphing this on your calculator, and you were to zoom in really, really close right here, essentially what you would start seeing is you would start seeing that your graph is getting more and more towards a straight line behavior. Okay? Here's the graph of the picture. You can imagine that us just sort of zooming in on that point right here. And if you look at this, the graph, if you zoom in far enough, basically looks like a straight line. Okay? So it makes sense for us to talk about how fast the graph is changing right here and relate it back to the slope of a line. Because that's what this graph looks like if you get close enough to it. It looks just like a line, and we can talk about slopes of lines. Slopes of lines give us a way of talking about rates of change. Okay? Now, we can also do this in a more systematic way. We can do this using some formula type stuff. Okay? Rates of change here, this again, average rate of change. If I want to look at sort of what an instantaneous rate of change looks like. Instantaneous rate of change, that would be like what happens when we let this interval that we're looking at get infinitely small. Basically, the difference between this point and the point that I'm drawing my line to, the difference between those is 0. We can do something like that. And what we're basically doing is, if we take our delta y and delta x, make this look like f of x plus h minus f of x all divided h. I'm going to say as h goes to 0. F of x is our function. Those are our y values. If we look at this, this is sort of giving us an idea of what happens as we get h really, really, really small. And what I want to look at is what happens to this whole thing right here. I can't let h equal 0, but I want to look at what happens as it gets very, very, very close to 0. And so what we're going to do is we're going to look at an example. Let's take a look at y equals x squared. And what I want to do is I want to find the instantaneous rate of change at x equal 2. Okay? I want to know that what happens, how fast is this graph changing when I get closer and closer to x equals 2. Now, all I'm going to do is I'm going to use this concept right here. I'm going to use this formulaic expression using this function and this x value, and I'm going to see what happens to this function. How fast is it changing at that particular time? Okay? So what I'm going to do, this is my y equals f of x function. Okay? So I'm going to take this, I'm going to plug it in here. I'm going to look at f of x plus h minus f of x all divided by h. I'm going to look at this. Now, what does that equal? I'm going to start by plugging in the things that I know. I want to know what happens at x equals 2. So I'm going to plug the 2 in here for x. Okay? So this is going to be f of 2 plus h minus f of 2 all divided by h. Okay. This is just symbols right now. Bunch of symbols, bunch of things that I need to replace with formulas or expressions that I know. What is f of the quantity 2 plus h? What's that equal? Right. All I'm doing is I'm taking this 2 plus h and I'm plugging it in here for x. Okay? So that's going to give me a 2 plus h quantity squared minus f of 2, 4, or a 2 squared, and then I'm dividing all of that by h. Alright, continue on. I need to try to simplify this, okay? As I try to let h get closer and closer to 0, I have a problem because I have a 0 in the denominator, right? I have something that's very, very close to 0 in the denominator. Well, when I divide by things that are very, very, very small, what usually happens? This whole thing gets very, very, very big. So I want to try to simplify this down a little bit more. See if there's a way I can cancel the h out. See if I can get that h to go away.
Could you use where
Okay, so they're squared here, and what do I get?
Factor out your h, and then cancel your h's out.
Okay, hopefully that'll take us in the direction we want. Let's see, if I factor, or if I expand this side out over here, 2 plus h squared is equal to what?
4.
Okay, so we get a 4 plus how many h? 4h. Plus an h squared, minus another 4. All of that divided by h. Okay. Then if I simplify here, what happens? Well, the 4's will go away. And lucky for me, everything that I have left has an h on it, right? If everything has an h on it here, what can I do? Well, this h will cancel with that one and one of those, and what I'll be left with is something that looks like 4 plus h. Now what does this mean? Well, this means that if I let h get very, very, very close to 0, how fast is this function changing at that particular point? Using this expression, I can see that as h gets really, 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 really small, what happens to 4 plus h? Right, as h gets really, really, really small, this thing is getting closer and closer to the value 4. For this particular function, if you were to, again, sort of zoom in really far and look at the slope of the graph at that particular point, what you would see is that the slope of that line is equal to 4. That's what this process is doing for us, is it's trying to find how much this particular graph, this x squared graph, how much it's changing at the very instant x equals 2. Right? Now, in order to formalize this idea, we need to work with something called limits, which is what the next section's on. But the idea is basically the same as what we went through here. We take a look at this expression right here. This expression is often referred to as the difference quotient. Okay? I'm looking at the difference of two function values divided by the difference in the x values they're associated with. Okay? This difference quotient, if I can go through and simplify things in this manner, I can try to identify how fast that particular function is changing at that particular instant. Okay? Let's take a look at another one real quick and see how we're doing. All right, let's take a look at f of x equals 6x plus 15. Okay? All right, and what I want to do is I want to find the instantaneous rate of change at x equals 28. How fast is this function changing when x equals 28? Some of you may have ideas, may know sort of what the answer is. Let's give everyone an opportunity to experience the joy and glee that comes from finding such a thing. So let's think, okay, how am I going to do this? Well, again, I'm going to go right back to this difference quotient idea. I'm going to look at what happens to this expression as the h value gets very, very close to 0. So what I'm looking at is I'm looking at, again, my f of x plus h minus f of x divided by h as h goes to 0 at x equals 28. Okay? This is what I need to evaluate. I need to evaluate what happens here. Okay? All right. Well, start by just plugging everything in. Okay? Change the expressions, change the values of x to the appropriate place, replace the f of functions with the appropriate function expressions, and let's just see what happens. Okay? All right, well, let's see. First thing to do, I'll replace the x's with the 28. So this is f of 28 plus h minus f of 28